All right, well, hey, everybody. It is time again for Astronomy Daily Live. It is 2:01 UTC, and I am hanging my head in shame because I am late. I am late, but yeah, you know, a good kind of late because we're all coming in here talking all things astronomical, and yeah, I've still got my new mic stand here, which looking like it's going to work out pretty well. I still have to sort of get comfortable a little bit with it, sort of pose around a little bit, make sure that I'm comfy here. But come on in, everybody. Come on in. See, I can do it with two hands now. Come on in. Join the circle of friends. Got some kitties in the background over there that are having a good time. Lots of kitties around here. They like to wrestle, so you might see that in the background from time to time. But yeah, they all have a pretty good time. So yeah, so hope everybody's doing well out there in the universe and the world. You know, always so much to talk about in terms of astronomy. It's never ending. So I see Tom in the chat, Atta's in the chat. Uncle Bill is on the panel. Hey there, Uncle Bill. And
hello, y'all.
Hey, Bobby's on the panel too. Hey there, Bobby. What's going on?
Yeah, thank goodness we dodged the bullet.
Yay! Just gotta. Yeah, cool. Hey there, David Sims. Nice to see you in the chat too. Really been enjoying your recent posts about calculating orbits. It forced me to actually. Let me go get it since you're there. Here, hold on one sec.
You're watching Sky Uses 2 live stream too, Uncle Bill?
Yes, I'm monitoring her channel also.
Yeah, I'm watching on the Roku right now.
So it's sort of David Sims inspired me to grab this book off of my shelf, and this is sort of what this is sort of my go-to book when it comes to all things, you know, celestial mechanics, right? I'm gonna pop that chat back in here, and yeah, I think I
studied that book.
Yeah, this is a brain killer, right? I mean, this is like this will take years off of your life, right? But it's very awesome, and I'm trying to let me see if I can find where. I mean, this thing actually goes through all kinds of stuff, and I actually looks like I got this book in December of 1992. That's where I put the date right on there. So pretty interesting topics here, right? Chapter 1 is fundamental principles and definitions. Chapter 2 is rectilinear motion. Chapter 3 is on central forces. Chapter 4 is on the potential and attractions of bodies. Chapter 5 is the problem of two bodies. Chapter 6 is the determination of orbits. Chapter 7, general integrals of the problem of n bodies. Chapter 8 is the problem of three bodies. Chapter 9, perturbation, geometrical considerations. And Chapter 10, perturbations, analytical method. And you know, this is some pretty intense intense text, right? Some pretty fun.
Also, celestial mechanics is one of my favorite subjects. If it really took years off of your life, I should live until 150. And David says that book will work. Try WGAD Determination of Orbits, Chapter 6.
Cool. You know, I found it very, very coincidental that that book that you mentioned there, David, is exactly the same chapter in this one. Right? Chapter 6. This camera's not there.
I think you just left your mic.
And I left my mic. So yeah, David's using the
Hewlett Packard Prime.
yeah, he's using that in terms of computation, but he's using the Gaussian method, or the Gauss method, Gaussian method, I guess.
David says attempted to do a link, but he's not a moderator. I think that's one of those YouTube restrictions. And also says that the law firm where I used to work as a patient attorney or a patent attorney, there were a lot of 3-body problems.
I did not even realize he was using Gaussian. I know a guy that does algorithms, not specific programs, and he's covering Gaussian methods this week on Twitch.
Well, for orbits or for other things, because Gauss, right, was this huge mathematician.
The Gaussian method in general, whatever the heck that means.
Okay. Yeah, I think there are, and David, maybe you can correct me if I'm wrong, but I think, Gauss was so, pervasive in mathematics that there are lots of Gaussian methods. But so, yeah, I mean, this one, specifically is determining the orbits. So, and maybe, David can correct me on that. I'm not exactly sure, but yeah, Gauss is everywhere, right? You've heard of the Gaussian distribution, right? That's another Gaussian type of a thing. So, hey there, Crystal. Nice to see you in the chat also.
Hey, Crystal.
Yeah, let me, David.
Gaussian type of a thing. So,
yeah, I can actually post your link. Let me go over to my Discord, and as top nerd here, I can do that. I have the power.
David sounds like Bolton does a long, slow build-up to orbit determination.
Yeah, it's, as David knows, it's a iterative process. And here's a link to David's code. If you folks want to look at that, I'll put it in the chat here. If you understand, programming languages at all, this is really, really easy to read. There you go. So yeah. Anyway, that sort of inspired me to grab this book off the shelf and page through it and remind myself about linear algebra, and it's like my determinants and oh man, all those other things. It's just I mean, really, really, really cool stuff. And actually, linear algebra is much easier to sort of work with and deal with if you program it than if you sort of work it out by hand. So, but you know, most of what celestial mechanics is you know, vector spaces and you know, a lot of differential equations, you know, that kind of stuff. Messy math there. So, but you know, if you're a math nerd, like to get into this stuff, it's pretty awesome and works really well. It's kind of interesting, you know. I'm always interested in trying to think about why, you know, what the differences are, you know, between models. And actually, this book, and I'll bet you the book that you mentioned there, David, also has the Laplace Method, which is just another way, I guess, of doing the same thing. I'd like to, you know, run all the numbers through and see what the differences are, and actually see, you know, what the differences are in terms of you know, the steps. You know, what do you have to do in order to get to a solution? But
now,
yeah,
does it have like Carl Sagan's brake equation?
no, that has nothing to do with celestial mechanics whatsoever, and that's actually Drake's equation. But I know what you mean. But yeah, you know, this book, it actually talking about, you know, the determination of orbits. I'm trying to get to that chapter. Conditions of circular orbits. Isn't it? It was chapter 6, wasn't it? No, it was chapter 6. Where's chapter 6? Oh, 191. Okay, I was just looking a little too far here. 191. So, yeah, what this actually does is it these things walk you through step by step. See, here it is. It says outline. It's not going to focus, is it? Come on, you. Focus. No, it's not going to. Anyway, outline of the Gaussian method, and then it says, you know, first step. And then somewhere down here it says second step, third step. You just have to follow all the steps, right? It's an algorithm. And so it gives an outline, and then it goes into detail. And yeah, you know, I mean, it's multi pages. So yeah, very cool to go through all that. And I'm going to take David's code. He's actually given me permission to do this. I'm going to take David's code, and I'm going to recode it into C. So, yeah, because I want to use it too. I don't have a HP prime calculator. I just have, I've had this calculator. This is a Casio FX300SA. I've had this calculator for at least 20 years. I want to say that I've had it for maybe 22 or 23 years or so now. And the calculator prior to this that I had was some kind of Texas Instruments, I forget exactly, and I had that for about 15 years before it failed. So I've had this guy for a long time.
So welcome, Crooked Ninja. David Sims, Carl Frederick Gauss got his name attached to a lot of methods. He invented the fast Fourier transform, for example, a long time before Cooley and Tukey were discovered in the 60s. And Uncle Bill Durham put that hitchhiker's quote in there. The answer to everything is 42.
Well, yeah, that's just a given. Yeah, that's a fact. Now, I did not know that Gauss invented the FFT. That's kind of cool because I've used the FFT. I mean, I've written code, you know, to do FFTs, and yeah, I didn't know that Gauss did that, but Gauss, man, oh, I'd like to learn a little bit more about him. You know,
David Sims, there's even a least squares method orbit improvement that uses a set of partial differential equations and issues observations to get better orbits.
yeah, yeah. Well, I know for a fact there are lots of different methods, and I'm messing with my microphone stand here a little bit because I've got a, man, you know, just like everything else in this place, I've got a screw loose. Let me see if I can fiddle with this thing a little bit. It's just how it goes.
Sometimes my family has a screw loose.
If I can get this in here. Yeah, that's all right. I'm gonna have to mess with that.
Man, way ahead of his time, says Altalada, in her honest opinion.
Yeah, I totally agree. You know, going through university courses and stuff, especially when you do all things astronomical and physics and all of that, you also basically, you know, go through all the math classes too. And Gauss was everywhere. Everywhere you turned, Gauss was there, right? And when did he? Let's take a little bit of a Gaussian tangent here, and I'm gonna share my screen, and let's just do a quick Wikipedia. Let's see, I got to get the right screen here. Let's get a quick Wikipedia on Gauss. See if we can just.
Okay, David Sands partial light ascension by partial semi-major axis times delta semi-major axis plus partial light ascension by partial incendiary times delta incendiary plus partial right ascension by partial ink.
Well, yeah.
That's Greek.
I think that's right. That's just calculus talk. Yeah. Yeah, I got to get the right screen for sure. All right, here he is.
Not a bit crazy. I didn't take calculus at school.
Carl Friedrich Gauss. So 1777 to 1855. Okay. So yeah, a couple of hundred years ago now. Pretty amazing. But yeah, you know, so they're saying, at least here, right, that he was a mathematician and a physicist. Algebra, analysis, astronomy, differential geometry, electrostatics, geodesy, geophysics, magnetic fields, matrix theory, mechanics, number theory, optics, stats. Yeah, you know, what are these people? You know, what are they? How I cannot fathom. I cannot fathom these kind of people, right? Just absolutely amazing. Absolutely, just yeah, crazy. But yeah, we'll have to check him out a little bit more. But yeah, you know, when you go through math classes at the university, Gauss and what's the other dude? Cauchy. It's C-A-U. This dude, Cauchy is everywhere. This guy is everywhere too. And, you know, they were contemporaries, right? But again, I mean, you know, his name is everywhere. Fourier is everywhere. Joseph Fourier. And again, contemporaries. These guys all lived around the same time, right? So yeah, just absolutely amazing. And you know, math is great. It's a great tool. It's you know, can get us into trouble though, right? I mean, it can box us in. It can enlighten us. It can also greatly confuse us. So, you know, if you lean on math too much and say, you know, this is reality, then oh, I don't know about that, you know. So cool. All right. Well, let's see. Let me. I'm gonna stop sharing. Stop sharing, and I'm gonna come back.
Anybody hearing my TV or no?
I'm hearing it just a tiny bit, but no big deal to me. By the way, I've got the coffee tonight, and see, I'm still having to learn. See, I can't do this. See, because the mic stand is in the way. I've got to do this right-handed now. And look, I'm out of focus. So I'm gonna. There we go. So I've got the coffee tonight in the nice heavy thick mug. Cheers. And I have the hydrogen hydroxide. So cheers to that too. Probably what I should do is get myself over on my smartphone so I can watch all the shenanigans from there.
Are you traditionally a lefty?
No, I'm definitely a righty, although I'm not completely ambidextrous, but I try very hard to do things sort of equally. But no, I'm definitely a righty. Yeah.
If you are naturally left-handed, you should be somewhat ambidextrous. That's all I wanna.
Oh, okay. Yeah. I actually live, the community around me, there is an unusually high number of left-handed people. Very strangely, you know, high percentage of left-handed people in my vicinity here. It's uncanny. It's really kind of strange.
It's not like a big crazy when you had to buy left mouses and trackballs for left-handers instead of right-handers.
Yeah,
so I got a trackball right now that's more like a right. It's meant for a right-hander and stuff.
Yeah, I gotcha. Yeah.
Seem to recall that one of the Hebrew tribes in the Bible had an apparently had a lot of lefties. Seems like everybody who came out of that tribe was a lefty.
Yeah. You know, and you know, this is sort of, you know, the debate about that, right? It's like, is that a genetic disposition or sort of a cultural thing? I mean, you know, are we told when we're really young, you know, no, don't use your left hand, use your right hand, right?
I am Ottawa's left-handed and can almost do everything with both hands, including pretty much, I don't know what she means about shooting, but probably like shooting balls, shooting pool, whatever.
Maybe shooting guns. Yeah, cool. Yeah, I've got a friend who is uh, um, he's a drummer, and he is right-handed, right? All right-handed, but he plays the left-handed drums. So the setup on the drum set, um, um, he
Okay.
plays it. He plays it
Pistola.
left-handed. So yeah, shooting pistols. Yeah.
Combat Skyder is also left-handed and somewhat ambidextrous. I've always assumed it was because many things are made for right-handers.
Yeah, well, that's sort of what I mean. It's like, what
Yeah, one
kind
of
of
my high school friends is ambidextrous too. She can do left and right.
cool. Yeah. I'm just wondering, if there are cultural pressures, right? To be for some reason right-handed.
Now, let me tell you something. We had to do like a little experiment one time while I was at elementary school. If you are right-handed, they will tie you. You have to be tied right at the back of your hand, and it's like one of those amputation exercises. And try to do everything you got to do with your left hand.
Yeah.
Let me tell you, so that thing was a son of a gun.
Oh yeah, I'll bet. I'll bet. Yeah, I guess being a keyboard player, I you know I use both hands that way, right? And so the left hand can be doing one thing, and the right hand can be doing another. And actually, one of the bands that I played, I was sort of the Ray Manzarek guy. So I was playing the bass with my left hand, and then melody and rhythm and everything else with my right. Yeah, that's probably why I can sort of do both. But I mean, I definitely favor um, the right hand. The right hand is much stronger. Um, I don't write with this hand. With the left hand, I don't do much with the left hand except play and. But as I said, I try to do both if I can. So, all right. Well, that was an interesting tangent. Let's get back to astronomical things.
Check the chat before you do.
And write the alphabet with your toes. Very cool. Very, very cool. Yeah, I've, I mean, I think that we are capable of many, many, many things. Hey there, Dr. WD40. Nice to see you in the chat. Welcome, welcome back. Come in a couple times, so nice to see you again. Come on in, share.
D-Dub's in the house.
Share the fun. Yeah.
Wow.
So very, very soon, in about half an hour or so, Fraser Kane over on Skylius's Twitch channel is going to be looking at the sky again. And I guess he is going to be looking at it with a different telescope. Now, is this in the same...
Now, how many remote telescopes he's actually got?
At the moment, I think there's just one. I was just going to ask that. Is this telescope mounted onto the same one that he was using before? Or do you know that, Uncle Bill?
I'm going to guess they're in the same facility or very nearby. I don't think Fraser actually owns any of these. I think OPT is just hiring them out to him.
Yeah, yeah.
He might be paying, a monthly fee, or they could be splitting the cost with him for the promotion. I don't know how that works.
Yeah, I'm not exactly sure. I mean, I was sort of under the impression that they were sort of, they're not, giving him the actual telescopes and cameras and stuff, but they're giving him, use of all these things. Just
right.
Donating it. So
welcome, Indy Cowley, to the chat.
Hey there, Andy. Nice to see you.
And they're put together and set up to spec too. So
yeah,
So there's got to be, you know, like a rental release kind of setup of some sort.
I see. Yeah. Well, that mount he's got for the refractor could certainly handle 2 telescopes. You just have to be able to, you know, figure out.
Good point.
Andy
How to
Kelly's
attach them.
Demonstration King got 3 he can use.
Yeah, I think they're setting up another one in Texas. Is that what I heard? I don't know if that one is running yet, though. So, yeah, you know, I'm sure we'll find out a little bit more tonight. And if not, I'll ask. So it's as easy as that.
I'd like to welcome Bill Wink. Not sure what you're all referring to. I just arrived in the 9th grade. I took all my German notes written backwards in cursive. They sent me the guidance guide. I haven't just been bored.
Yeah, you know, Bill Wink, nice to see you. Welcome, welcome, welcome. This is the Astronomy Daily Live. We usually talk about just astronomical things, but for some reason we got onto this left-hand, right-hand thing. Yeah, for a short amount of time when I was younger too, I used to write backwards, just for fun. Right?
I used to write square numbers.
Cool. Cool.
Yeah, but the teacher wants me to slap me in the face and stuff, send me to the principal's office and stuff.
Yeah. Anyway, so Fraser's going to be using a new telescope tonight, apparently. And I was able to actually find a white paper all about that scope and sort of the history of the scope. It's called the Schmidt telescope. It's a relatively simple design. It just uses one mirror, sometimes a corrector plate in the front, and then you put your camera or detector at this location called prime focus, which is just the focus of that main mirror. So let us go over.
Kind of accomplishment, Bill. The kids are not even taught cursive anymore. Backwards or forward, says Atalana.
Oh, really? Yeah, you know, I fought against cursive when I was forced to learn that, and I fought it because it's like, what exactly is the point here? What exactly is the point?
Okay, and, so David Sims, Gauss didn't publish his FFT algorithm. He kept his secret so that he could be the only one to do spectral analysis. It was later found in his notes after he died.
Oh wow, that is mean. That is. I guess
mean. That's around on yours and stuff. Is FFT and stuff.
Yeah, that is mean and cruel, but a great advantage. Yeah, because the normal way of doing a Fourier.
Hey, at least he kept notes, right?
Yeah. Well, you know, that's a mathematician for you. So yeah, for sure, for sure. But yeah, the normal way of doing a Fourier transform is really complicated, and you know, to come up with a faster way, you know, you have to follow certain rules in order to do a fast Fourier transform. But yeah, they certainly are incredibly faster. Yeah.
Okay, you better want to check the chat again.
Yeah, I'm looking. Yeah, high humidity. Yeah. Florida is definitely not a good place to do anything astronomical, for sure.
Yeah, it'd be a real. Whoever had to maintain that scope had his work cut out for him.
Yeah, that's a little rough. Anyway, so Fraser's going to be using this telescope tonight. I'm going to show.
Dr. WD-40, are you talking about the University of Florida or what other university in Florida?
I guess we'll find out. Where is it? There it is.
I didn't even understand the question, Bobby. Say that again.
I was asking WD-40, is that in the University of Florida or like Miami University in Florida or what? Oh, Florida Institute of Technology. Thank you.
Fit. He's going to have a fit. So, big, fast, wide.
F2.2. Wow.
Yeah.
Wow.
You know, F2.2 actually really isn't all that fast. I think most, I mean, my C8, I'm sort of looking at my C8 over there. It's probably not much more than 2.5.
Oh, yeah.
Or so, right?
Really?
I mean,
What's the difference between Florida Institute of Technology and Fashion Institute of Technology?
I think there's a little bit of a difference there, Bobby. Hold on a sec. I'm going to get this this bag off of here. So if you look at that width, right? I'm going to try to do it here, right? If you look at that width, see there's, well, yeah, it's going to be hard to do that. So there's about a width, right? More or less. So there's one, there's two. So
but
this
there's
is
a double reflection in there, isn't there?
Well, yeah, the secondary mirror is concave, and so that actually makes the focal longer.
Okay,
But the focal length of the primary
that's the reason why we had to buy the FIT rights from the Fashion Institute, which is in New York.
I see. Cool. That's cool.
And,
but yeah.
Now, what's going to be our plans of viewing sky ellipses? Are you going to be like in their chat, or you want to rabbitize it, or what?
I think I'm just going to go in the chat. Yeah, I think that is the way to do it.
You too, Uncle Bill?
We talking about sky ellipse?
Yeah.
Yeah, I'll go there directly. Okay, so back to your scope. You're saying that
the primary
secondary mirror is acting like a focal extender?
Exactly.
Okay.
Yeah. It actually lengthens out the focal length. It changes the focal ratio, right? So yeah, this primary mirror, as I said, is probably really close, to f 2.5 or so. So to sort of make this a Schmidt camera, not exactly, but you would just have to put the CCD camera or your camera right up there instead of down here, right?
Yeah.
There are other subtle differences there. I think the shape of the mirror is different. I can't be exactly sure. But let's look at the white paper really quick. It's actually pretty long.
Yeah. Say I'm a geek for the cheap, not Dobsonian Newtonian. So anything under 4 is pretty fast for them.
Oh, it is. It is absolutely. That's absolutely true. But C8s have always been about that size and about that focal length, as long like in terms of the primary mirror. So yeah, I'm not exactly sure if this is the one that he's using or not, but the
Twitter did say Celestron, and it did say RASA, which Google tells me is a RASA. So exactly what you're looking at there.
Yeah, yeah. So yeah, I just found this, by I'm doing a Google search, and this is April 2016. So maybe there's a newer version of this or not, but yeah. So here's sort of the standard Schmidt camera, right? Which just has, and they're not showing the inside here, but there's a primary mirror here, and then they, at the time, of course, they just used photographic plates, and those plates probably were around here or so. But yeah, that's how we did our first surveys. The POS plates. Yeah, I actually got to see those big, huge glass plates that you sweat when you carry around. The one thing that I hadn't heard of was this term attendu. I guess that's how you pronounce that. Now, apparently it's a familiar concept with opticians, but I've never heard of that. So let's see what it is. It's the energy flowing through an optical system. So this value, right, is the collecting area multiplied by the solid angle field of view. Okay, all right, I got you. Yeah, so it is. It's just all, well, it's a measurement of, I guess, of like volume, right? It's just all the light, all of it. Okay, kind of cool. So it's units are a little weird, right? Meter squared, degree squared. So, okay, all right. So the 48-inch Schmidt camera up on Palomar had an attendu of 46. Cool. Okay. Kind of interesting. Yeah, I'd never heard that term before, so that's kind of cool. Anyway, let's sort of get into this a little bit more. There's the LSST, at least a model of it. Let's see what that, so let's see. Oh, okay, so these are more modern sky survey telescopes, and we can sort of see what the size is of the primary mirror and then how much of the sky it actually sees, square degrees, and then here's that attendu value. Look how the LSST just stands out. It's just absolutely huge. Absolutely huge. And, that's mainly because it's a big mirror and a big piece of the sky at the same time. Kind of cool. Yeah, so there's a fast star, right? So that's the basic idea, right? Is that you put your camera here, and it's still, not going to obscure the primary too much. Of course, it is a little bit, but most of the area of the primary mirror is on the outside, right? So you're not really losing a lot of light if you block, the central part. And that's why, the Schmidt-Cassegrains work okay, because the secondary does actually block, part of the primary, but in terms of the area blocked, it's actually not very much. It's a pretty small percentage. So here's an 8-inch f1.5 Schmidt camera. So there you go, Uncle Bill. That's nice and fast. f1.5.
Oh, wow.
Here's the Palomar telescope, right? 200-inch. And a lot of the instrumentation they did actually put up at the prime focus. Of course, here's a guy sitting in the cage up there. Here's the Hyperstar. You can hear your TV a little bit, Bobby. Turn that down a little bit, please.
Okay.
You might be hearing me now.
I might be hearing you. Anyway, I hear something in the background.
Yeah.
I turned mine off just in case. I don't know.
Okay. Appreciate it. So the Rasa is conceived. David Rowe, Mark Akermann, who conceived and refined the optical design. So there it is. There's the... Okay, so it actually uses a series of lenses here. Oh, cool. Kind of neat. So it uses a corrector plate, and that gets rid of a lot of the, rainbowing effects and all of that. Now, it doesn't say here if this mirror is a spherical mirror or parabolic. Not exactly sure. Might be able to find that
Hey,
out.
what's up, Hip?
Is Hip in the chat? Cool. Hey there, Hip. So, yeah, light from the object, of course, it comes in here, bounces off the primary mirror, and then goes into this series of lenses, and that's where you put your camera, right there. Kind of cool. So they're calling it a 4-element corrector lens. Okay. Pretty nifty. So these are spot diagrams. It's been a while since I've read these. These are different wavelengths, right? I guess these are in microns, right? So to an astronomer, this would be 4,360 angstroms, right? And 4861, 5,000 angstroms, 54, 6,000 angstroms, blah, 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 right? And they sort of colorize them in a nice way there. And this, I'm trying to remember what these are. I think this is, okay, yes. So this is just looking at the off-axis. So as you move more and more off-axis, what does a sort of a single point, how does that distort through the optical path? And as you can see, it distorts, of course, as you move around, but it also distorts depending on what wavelength you're looking at too. So that's kind of interesting. And I guess each of these boxes is 9 microns. I guess that's how I'd read that. Because there are some smaller boxes in here too, a little grid. So I'm not quite sure if these smaller boxes are 9 microns or if this big box is 9. I'm sort of thinking that this big box is 9 because 9 microns is sort of a typical size of a CCD pixel. So that's sort of a educated guess there on that. The bottom line here is, right, is that all of these, regardless of the distortions, right, all of these are falling on a single 9 micron spot. So all of these are going to hit you know, 1 pixel, which is that's sweet. That's really, really nice. If you're able to do that, you've got a nice system there. So there's a corrector plate. That's sort of a big one. That looks like an 11-inch maybe. It's kind of big. So yeah, Rasa is just a modification of the Schmidt. And I'm saying just a modification of the Schmidt. I mean, this is pretty awesome. So I'm not trying to belittle that in any way. Why don't I'm going to post this in the chat, and I'll also post it over on Discord so everybody can take a look at that. Oh, I guess I've already got it, but I'll do it again. Copy live stream chat. Okay, so it's over on the Discord now too. So just so you can have it there, look at it yourself. So I guess, you know, the focusing is still in the back, right? So it's still moving primary mirror in order to focus, right? So if we go back, here to this, right, the focusing knob, I don't know which one it is going to move the primary mirror back and forth in order to focus, as opposed, you know, to moving any of this, right? It's just a lot easier to do it that way for sure. Let's see, focus. I'm kind of interested in knowing what's in here. Here we go. So the 12-volt DC maglev fan, along with improved venting. Okay, so so it's just a cool. Okay, so it's just a fan to keep the telescope and all the optics at sort of the same temperature as the ambient air, right? I mean, these are objects, so they like to collect heat, but they've stuck a little fan in there to blow some of the air around, and well, that's kind of neat.
Yeah, now I can understand ventilating behind the mirror, but I've never understood if you've got air moving around in the tube, isn't that going to amount to the same thing as force seeing? Is that not going to cause refraction effects?
Yeah, I think it might. I have to think about that. It sort of looks like it's venting off to the side, sort of behind the primary mirror. So,
right.
Yeah, I don't know.
I don't know. Makes sense.
Yeah, it's a good question. Don't know.
Of course, when dew's an issue, it's just, it's the lesser of two evils.
True.
It's like us putting heating elements around the, our front lenses on refractors and stuff.
Right.
A little bit of that, less detrimental to your image than dew.
Yeah. Very true. Here they're showing a little bit of the manufacturing and testing part. So here's all the primary mirrors back here, and they they use some kind of interferometry to measure the surface. There are two things that you're interested in with mirrors, right? You want to make sure that they have the right shape, the right curvature, right? That's pretty important, right? I mean, if you want an f 2.2, you've got to make sure that mirror is curved correctly, right? And the second thing is that it's got to be really, really smooth, right? It's got to be polished really, really, really smooth. So those are sort of the two things that you look for when you're doing any kind of testing of optics, is that you want the curvature to be right, and you want it to be really, really, really smooth. And a really, really smooth mirror is going to have bumps that are no larger than about 1/10 of the wavelength of light that you're dealing with, right? So if you're dealing with visible light, right, that's about 500 nanometers. So you don't want any bumps higher than about 50 nanometers. And those are really tiny, tiny bumps. So yeah, you know, these things have to be really, really smooth. Now, 1/10 wave is like really, really, really awesome. Normally what you get is about 1/4 wave or so. Quarter wave is you know, good enough. It's not really, really awesome.
Yeah.
It's not really, really, really bad. Quarter wave is sort of a nice sweet spot, because, you know, as you polish all these things, it takes time, it takes material, and it gets more expensive, right? So quarter wave is sort of a nice compromise there. What were you going to say, Uncle Bill?
I was just going to, you know, I followed a lot of the amateur telescope makers. You know, it's kind of gotten out of style these days. But, you know, we still have a awesome website for the Cellophane group.
Cool.
And if I'm not mistaken, they tend to boast of up to 1/8 of a wave accuracy with just garage-built stuff.
Yeah.
Now, of course, a lot of these guys are probably building their 5th or 6th telescope by now.
Yeah,
And
you know.
Akermann also said that capturing impressive deep-dry astro images is easier than ever with Celestion's new Rowe Akermann submitted Astrograph, the perfect companion for today's top DSLR or astronomical CCD cameras, and he's actually asking Ottawa if they check the chat.
CCD disposable camera? No way. Really? Wow. Interesting. Wow. This is like
that's got to be a typo. But HIP actually, if I'm not mistaken, I don't know if she said she's got one yet or not, but Ada at this point is still concentrating on what she can see with her eyeball.
Yeah.
She's still getting the knack of the telescope itself before she starts messing with the camera stuff.
Yeah. You know, go at your own pace. That, you know, have fun. That's what it's all about. You know, if it
exactly.
You know, if it's starting to get, you know, frustrating and not fun, you know, put it away for a little while. You know, catch your breath. Because, yeah, you know, it's not supposed to be a race or anything. It's supposed to be a little bit fun. And it is going to be frustrating for quite a while, right? But, you know, you have to be a little bit stubborn, and you have to stick to things. But Atta, I don't think is going to have any problem with that. No problem. Okay, so here's some more.
She's been learning very fast, and she's been going one step at a time, and shows every appearance of having a ball doing it. Winter weather lets her.
Yeah. So there's some more testing. I'm not quite sure what they're doing there, but final acceptance test, I guess.
Almost looks like a knife edge test rig, but not quite.
Yeah. Not quite sure why they have this there. Maybe it's to actually create, you know, some kind of diffraction pattern, so they can, you know, test things here. You know, they got a camera on it, here. So yeah, sweet, nice looking camera. So it looks like they have at least two different sizes, right? They have a 14-inch and an 11-inch, and yeah. Let's see. I sort of have a classic C8, right? Classic C8 is that guy, and so the attendu for that is 252, and now the sizes here are different, but yeah, those numbers are pretty impressive, and that's what you get, right? I mean, when you're looking at prime focus with such a short focal length, what you get is a very, very, very wide field of view. As you can see, 9.5 square degrees, right? So that's like 3 degrees on a side or so. And for a refractor or reflector of that size, that's impressive. That's a huge field of view, right? I think the refractor that Fraser is using right now is actually about that same field of view, but that's with a refractor, a pretty fast one. But this is with a much larger scope, much larger, same field of view. And as I said, I'm not quite sure if he is using a 14 or the 11. It's probably an 11. I don't know. We can ask, or he'll probably tell us. But even the 11 here, right? Pretty big field of view. Pretty big.
Yeah. Underwater, I have a go in mind. I'm going to put out a greedy astronomer out of business who charges for second-rate store parties at the old age community where I live.
Yeah. I have a few. Yeah.
That's horrible.
I actually have some thoughts about that. I should talk about that because actually after our conversation yesterday during Bobby's Hearts of Space thing, I was actually talking to my wife about it, and she made some interesting points. She usually does that. She sort of makes me think a little bit. So yeah, I should probably talk about that during the live stream at some point, because yeah, charging to look through a telescope, that sort of bothers me a little bit. But yeah, let's talk about that at some point during the live stream here, because yeah, I can go on a little bit of a rant about that. So anyway, nice wide field of view with a big mirror, right?
Her star party is going to be better and free. And Crooked Ninja said I would have to sell the car for that soap.
Oh yeah. No, these are not cheap telescopes. Definitely not. Definitely not. These are expensive toys. Expensive toys, but pretty nice. Anyway, then they get into cameras, the different kind of cameras that can be used, and what to expect in terms of imaging and all that. They've got a dew shield and a heater strip. You can actually put a DSLR on there. Now that, I would say, is starting to sort of obstruct the view a little bit, and it's actually this shape is actually going to make the images of your stars look a little funny, right? They're not going to be sort of round points. They're going to have some weird shape, but that's okay. That's all right. It's still collecting a lot of light, so no major worries there.
Pretty interesting. There, you could do it with a DSLR camera.
Oh, sure. Yeah. Yeah. Using DSLRs now in terms of astrophotography, that's sort of a very, very common thing that's being done. In fact, people are using their smartphones. So, yeah, pretty impressive. It's obviously a much bigger scope than what he's been using. So, he'll be able to take actually shorter exposures and get the same thing, or longer exposures and go a little bit deeper in terms of details and stuff.
I'm hearing Uncle Bill's on the background and stuff.
Background alert, background alert. All right, well, cool. I think, this is sort of a long white paper, but most white papers are really, really, really interesting reads because it's a little technical, but it's also, there's a lot of explanation and there's a lot of pictures. I mean, I like that, right? So there you go. There's a nice setup there with the dew cap and all of that. Really sweet. Really, really sweet. There's another shot there. Cool. Cool, cool. All right. Well, I think it's about time to get out of here because I'm gonna.
Almost. There is one thing.
Yeah.
Now, that first scope was a refractor because Fraser's just nuts about refractors, and he insisted on that. But now I'm getting the impression that was the second scope is now that Dustin's seen what the need is. He's the one that's pushed for this other scope that's even faster.
Yeah.
And I'm guessing that's a lot more aperture than the refractor too.
Yeah. Well, like I said, these telescopes seem to only come in two sizes, a 14-inch and an 11-inch, and that's significantly larger than 127 millimeters. So yeah.
Right. So the whole refractor argument. I understand refractors when your primary target is going to be planets or even the planetary nebulas that Fraser really loves. But these big objects with the galaxies and stuff, the Schmidt Cassegrains and reflector types make a lot more sense to me too. Yeah,
they're light buckets. So if you want to be able to see galaxies, right, which are inherently pretty faint, except for a couple of them, you need you just either need a larger scope or you need a longer exposure, and since he sort of wants to zip through a lot of objects, just makes sense to do shorter exposures with a bigger scope. So yeah, Dustin is right on top of that. So very, very cool. All right. Well, speaking of them, I think I'm gonna get off and join them over there. Join the chat over there on Skylius's Twitch page. Don't know, is he on yet? Has anybody been watching?
No, she looks like she's reviewing a YouTube of an astrophysics lecture or something right now.
Okay, yeah, it's definitely, I would say, really, really close to being
and
dark
there's
enough.
the link to her channel in the chat in case anybody hadn't found it yet.
Cool. Thank you very much, sir. All right. Well, I think I'm going to get out of here for now. So, yeah, let's do this again. Let's do this again soon. By the way, let's see. I'm going to look at my calendar here. I'm going to be doing a star party for my coworkers in a couple of days. So it's possible, depends on clouds, right? It's possible that the live stream will not happen for the 8th of September. Possible. It depends on clouds. I'm not going to know, I mean, I'm going to make a decision, like a couple hours before we start. If it looks like it's going to be clear, I'll definitely post something in like the Discord, and maybe I'll make a little video here too, just saying, it's canceled. But yeah, I think at this point, I would say there's about a 50% chance that I will not be doing a live stream for the 8th, and that's in a couple days, right? It's just a couple days away. So just warning you, that I'll be doing a star party for some coworkers and friends, and that of course is going to run into this time slot. So yeah, may have to cancel that. As I said, right now, looking at the weather, sort of a 50-50 chance, I would say. It could go either way at this point. So, all right, friends, I'm going to let you go. I will see you, definitely, for sure, in a little less than 23 hours from now. Just a little less than one dizzying spin. At this latitude, I think I'm traveling about 800 or 900 kilometers per hour, and
wow.
No, I don't feel a thing. I don't feel a thing.
I don't either.
Yeah. What? I don't know. But if you take a telescope out and look at a star, right, and don't track the star, but just look, right, you're magnifying that object, right, and what you can actually witness the rotation of the Earth that way. And once you see that,
here's something that's even wilder.
What's
Me
that?
and you don't even share the same vector.
No.
Yet our distance never changes.
It's just
If one of us gets in a car.
it's absolutely dizzying. Absolutely dizzying. All right. Well, with that, I'm going to go lay down, and I'm going to get over to Skylius's Twitch thing, because I want to see what this scope does too. So all right, take care, everybody. I will see you tomorrow. Thanks for coming. Bye.
Later.
Later, nerds.